Our study of convergency simply considered the great circle track. The rhumb line was not explored. However, there are some applications where we need to consider both the great circle and the rhumb line, and to calculate their difference in track angle. We need to look at this difference, which is known as conversion angle. A spherical Earth is a three-dimensional situation, but it is easier for us to draw representational sketches on flat paper in 2 dimensions. We need to understand that any 2-dimensional model will lose some of the characteristics of the original. This is not a problem, as long as we understand the limitations of our models. This 3-dimensional graphic represents 2 meridians on the Earth's surface, joined by a rhumb line, the parallel of latitude joining 2 points on the meridians, and the great circle between the same 2 points. On the 3-dimensional graphic, you can see that the meridians are not parallel, and that the great circle track is the shorter route. We could choose to represent it with a diagram showing the meridian convergence. The great circle is shown in green and the rhumb line in red. The advantage of this representation is that it shows the meridians converging and the great circle as the shorter line. However, a disadvantage is that it is not immediately obvious that the rhumb line is the one with the constant track angle. It looks as though it curves on this model. You need to realize that the orientation of the meridian defines local true north, and that as we move from east to west, the orientation of the meridian alters, rather like a swinging pendulum, still cutting the rhumb line at the same angle. And that the great circle, which actually looks like a straight line on this model, is the one which actually changes track angle. The great circle track angle here is not the same track angle here. A way of avoiding this would be to change our diagram from this to this. Unfortunately, this also introduces some limitations. The meridians are now shown as parallel when they are not, and the great circle now looks like a longer distance than the rhumb line when it is not. But the advantage of this model is that it is easier to see that the great circle is the one which changes track, whilst the rhumb line, which remains a constant track, is a straight line on the model. Some students get on more easily with the first diagram, whilst others find the second easier. We shall use both in the scenes which follow, but remember, neither of them completely represents the true situation. Imagine 2 meridians, let's say 20 west and 20 east, separated by 40 degrees of longitude. The parallel of latitude of 30 north forms a rhumb line joining them. The same 2 points are joined by a great circle. By how many degrees will the great circle track angle change? We use the convergency formula. Convergency equals the change of longitude times the sine of the mean latitude. The change of longitude is 40 degrees, and the mean latitude is 30 north. The sine of 30 degrees is a half. Try to remember that. It often comes up in these types of questions. So the convergency is 20 degrees. But we don't know what the great circle track is in order to change it by 20 degrees. However, there is a way to work it out. Now we know that the rhumb line track is 090 degrees true. It is a parallel of latitude. So the great circle track at midpoint must also be 090 degrees true. Now, bear in mind that in the northern hemisphere, tracking from west to east, the track angle will increase. Remember the DIID rule. If the great circle track increases by a total of 20 degrees and is 090 in the middle, what is its initial track? And what is its final track? If the track angle increases by 20 degrees and is 090 in the middle, it must start on 080 degrees and finish on 100. The definition of conversion angle is the difference between great circle direction and rumline direction joining 2 points. So we can now calculate the conversion angle. At A, the great circle track angle is 080 degrees, whilst the rumline track is 090. The difference is 10 degrees. It is exactly half the value of convergency, which, if you remember, was 20 degrees in this example. What about at the other end? There, the continuing great circle track eastwards is 100 degrees true. And again, the rumline track is 090 degrees. Rumline tracks don't change. Again, the difference is 10 degrees. If we take the reciprocal tracks from 20 east to 20 west, the track directions are 280 for the initial great circle track and 270 for the rumline. Again, the conversion angle is 10 degrees, exactly half the value of convergency. This gives us the formula for conversion angle. It is half convergency. Conversion angle is half the change of longitude times the sine of the mean latitude. Don't get these two mixed up. Convergency is the change in a great circle track. It has nothing to do with rumlines. Conversion angle is the difference between the initial or final great circle track and the rumline track. Here is a practical example requiring calculation of conversion angle. Firstly, determine the value of convergency between J, which is at 58:12 north and 4 degrees west, and K at 58:12 north and 6 degrees east. Then, what is the rumline track from J to K? Finally, what is the initial great circle track from K to J? As always, try to visualize the situation. Draw a diagram. Either of these will do. Let's solve the first question first. What are you going to do? Write down the convergency formula and substitute in what you know. Convergency equals the change of longitude times the sine of the mean latitude. The change of longitude is from 4 west to 6 east. That's 10 degrees. Now we need to calculate the sine of 58 degrees and 12 minutes. This may be the first time you've had to deal with a trigonometrical function involving both degrees and minutes, as opposed to decimal degrees, so we'll take a moment to deal with this. You could simply realise that 6 minutes of arc is 1/10 of a degree, just as 6 minutes of time is 1/10 of an hour, in which case 12 minutes is 0.2 of a degree. You can then just key in 58.2 degrees into your calculator. However, most scientific calculators have a DMS key. It stands for degrees, minutes, seconds. Different models work in different ways, but in general, you key in the degrees, press the DMS button, then key in the minutes, and press the DMS button again. We don't normally need the seconds. Find out how yours works and it will save you time. But however you do it, Don't treat 58 degrees and 12 minutes as 58.12 degrees. It's a common mistake.